Okay.
Okay, let me introduce our next speaker of our session on continual learning for explaining and NeSy, where we will have three amazing speakers today. And the first one is going to be Hava Siegelmann. She's professor of computer science, director at the Biologically Inspired Neural and Dynamical Systems in the University of Massachusetts, Amherst, and she's also being DARPA Program Director for AI, where she oversees the Guaranteeing AI Robustness Against Deception program and their Lifelong Learning Machines program. One of her initiatives, inaugurated as the third wave of AI, is pushing major design innovation and a dramatic increase in AI capability. And she also got the Obama Presidential Brain Initiative Award. So without further delay, I let you the stage. Hava.
Okay, great. Thank you so much for inviting me and waking me up at 6 a.m. I'll talk today about lifelong learning, about my view about the topic. And I hope next year we'll see each other. So in general, when we look at AI, there sometimes is a confusion, because on the one hand, we see all these beyond human capabilities that are shown to us in games, in classifying images from picture. And this usually we see with the cloud computing and with very structured environment. Usually it's on a screen. But when we take the AI to the outside world, we start finding all kinds of issues, and they're not always that trustworthy. And one of the chief source of untrustworthiness in AI is that AI is really frozen after it is done programming it and it is done training. So AI only does what it was taught to do in advance, in the lab, by the people who either design it or by the people who collect the data on the areas where data is. Now, if the word is not similar enough to what is trained or what is programmed, that can be a problem. And when you take it to the real world, there is no way to prepare for any possible futures. You can train for a lot of possible futures. But if you're in other situations, then malfunctions may happen. And one of the way we can think about it is that in AI that is kind of regular state-of-the-art AI, if you look at the y-axis is performance and the x-axis is time, we can think of, but the AI is being improved all the time when it trains, and that's it. Then it stays constant. If it's a new situation, it cannot learn from the new situation. And if it doesn't know what to do, it may crash. What we want to talk about is a lifelong learning. And the main feature of lifelong learning is it can improve with experience. And it's more up to date to what's happening around, because it's open up to environment and it tunes itself because it wants to continue to improve. So it takes a better understanding of what happened as we go. And this was the basics in the lifelong learning machine program that I founded. It was almost 4 years ago, so we're almost talking history. And there are a few pillars that I defined for this program, and I'm going to show here only the 4 most important ones, but in a longer talk, we can talk about others. So the first part of lifelong learning is that we want to have continual learning. So we want to expand our knowledge. So if I learned something during training and I continue seeing more things, more tasks, more classes, I want to be able to be open and continue learning. So I want to expand my knowledge after the AI is done. So if it's a child, it's not enough to finish 2nd grade. We want it to continue learning life in school. Then the second pillar of lifelong learning is the internal exploration, or what if. That is, since lifelong learning has to learn through its life, it doesn't learn only from the output, that in input that is given. So it's not just a reactive, it actually can make its own question answer. So it can make its own training set. The next feature of lifelong learning is that we really learn modulated programs. So that means if I learned a long time how to drive my car, and then I go to another state and I need to rent a car, and it's similar, but it's not exactly the same, I should know very fast how to change the driving of my car to the driving of another car. So this is a context modulated computation. Also, if I'm driving on one road and now I need to drive on another road. So the basics that I have, I can use them to have something more. And that saves a lot of time in computation. And all this is not worth if we cannot see new behaviors coming over time. So we really want to have more capabilities, to have AI that is more trustworthy. So just to say that one of the reasons that I started with lifelong learning is because I wanted AI that is more trustworthy. This was really the initial focus that I had, something that is improving all the time, that it's somewhat aware of what's happening outside. And all the rest really folded into this feature that we would like to have. So there is one particular feature in my mind that, I mean, there are a few features that make the difference between continual learning and lifelong learning. At least in the United States, I know that there are people that use the terms, confuse the term, but from my point of view, it's very different. So for continual learning, if we learn to separate between 0 and 1 and then between 4 and 5, we'll be doing it very well if we use continual learning methods. And this include elastic weight consolidation, synaptic intelligence, learning without forgetting, context-dependent gating, generative replay, and there are a few others. But so the notion is that I learn to do 0, 1, and then I learn 4, 5. Then if I given two numbers, which are 4, 5, I will know very well to separate between them because this is one of the tasks. But what I will not be able to do is to separate between 0 and 4 because there was no tasks like that. And in reality, if you look only at continual learning, sometimes it's dangerous because some continual learning algorithms actually reduce the generalization of the system. It allows more generalization to more 4 and 5, but it does not allow us separate between classes of different tasks. And some are even worse than regular neural network. And one of the way to solve it, which I was part, but the first authors is Guido, who is the postdoc who did really the large majority of the work, is the notion of storing or retraining. So one option is that we store data and retrain. So when we go forward, we retrain on previous things so we don't forget them. So we don't need to retrain everything from the beginning if we train it on the go. And one way that was suggested is to replace, instead of actually keeping the data, there is not really a way to keep a lot of data. So one way is to have a generator that once we start learning new things, it's once in a while remind us things that were already learned. So this way we can have some of generative replay. And the particular way that we liked is brain like generative replay. And this is actually a very interesting idea. The notion is that we put them together, the generator and the new model, in the same layers. But the interesting part is that we don't need to generate all the way to the end. In reality, when you generate all the way to the end, it's very hard method because, you know, generators are very hard to train and they're very sensitive for many things. But if you generate just a few layers, it's kind of like you generating an abstraction because you don't show the input. It's not like dreams that you have to see the input. It's more like a concept of general abstraction, and then you relearn just a very little bit. So these are like examples of things we would generate halfway. It's really very hard to see what they are, but these are enough to give us what we want in the idea of forgetting less and having this class incremental learning, which this is what we want rather than the task incremental learning. This is what we really want from intelligent system. There are few newer work on generative replays that are really interesting in the last 2 years. But I want to go to the other thing that I mentioned, which is internal exploration, because internal progression is a very important feature to gain lifelong learning. So internal exploration is that you do something from the outside, but the shadowed arm that you see here is what the model thinks about itself. And after some time, it manages to think about himself the right thing. So what is very useful, if you now change the arm or you change the task, you can relearn very, very fast. If you change the arm, you realize very fast that something doesn't fit here. You identify very fast that the internal prediction are not like what's happening on the outside, and you retrain what you need. So this is one way of internal exploration. Another one is to create your own training. Like, let's say I don't have more data of input output, but I can take an image that I already have, and I can take a piece out and say, what was supposed to be in? Well, I have the answer because I have the image, but I can ask myself, I can take an image and say, are these the right colors? So I can start taking things that I already have and kind of pushing the envelope. What does make sense? Which elements were in the same scenes in the past? So they kind of look in the same colors. But if I learned that a train station and a train have some relationship in many images, then I did a lot, and that can be really useful. What is also really important when you evaluate lifelong learning, that you don't do the same task. So in many papers in the past, you were learning lifelong learning, and then you evaluated on very basic tasks that are there anyway, and that you don't really need lifelong learning for. So maybe you got a little bit improvement. But what is really important is to do lifelong learning on situations that change. So for example, SRI group, they took the StarCraft 2 interface and started playing, but they're in the back. So as we played, they started having changing terrain. So you go around and then it changes. Then they also altered unit capabilities. So, you thought you're going to win and then it doesn't work, or switch friends to foes in the middle, move the goals, increase weapon range. So these are really hard things. And as you play and you start seeing that things are changing, and you move to L2M, you are better in doing that later on as well. So kind of just to summarize, the program Lifelong Learning will continue until this summer. I'm already out of DARPA. I'm already for a little more than a year back to Amherst. But in that program, there are lots of focus on biological systems. And in fact, some of the systems that people suggested are made of biological cells. So they created all kind of robots made of, frog skin or, whatever. It's all from different skins. And they have very interesting features because they're based on some biological features that are there anyway. So this has been very, very interesting to think about. Now, in order to have good lifelong learning, if we think about it, there are a few other features that you want to have. One is, when you have AI, you can have this adversarial AI, which is, this known trick that really trick the system exactly in its capabilities. So if the system can identify very small images, you send the vehicle and on the top of it, you put little images of cows smiling, and the AI will tell you that it sees a herd of cows because there are cows coming towards you and moving. So all these things are part of the confusion. And my second program that I was in DARPA, which will continue for 3 more years now, is the GUARD program, which is Guarantee AI Against Robustness. But when we talk about lifelong learning, there are some tricks that can happen, because we know that in GUARD, in deception, one of the tricks is to try to give training inputs, or to try to put over the internet all kind of images that confuse us. And in lifelong learning, since we're open to see what happened, this can happen more. So the question, how to protect lifelong learning, and the GUARD program is doing part of that, but there is more work that is needed in this direction. Another thing is the human in the loop. So sometimes in lifelong learning systems, since they're AI is not fully relied upon yet, is to have human in the loop, but we have to do it in a very smart way. So not the human will do the computation, but the human will have very particular roles. And I'll show you some ideas. We want to have this environmental awareness. It can be space awareness, time awareness, various features of awareness that are really important part of the feature of lifelong learning. And the other feature that also is very important in lifelong learning is the partnership between symbolic and sub-symbolic information. And the reason is when we transfer symbolic information between us, we can do it very fast. When we try to learn from examples, it takes much more time. So if there is a way that either the human or somewhere else will be able to tell the system something very, very fast, hey, beware, you're going to see something, and the system is able to incorporate this knowledge, then our lifelong learner will be safe. So these are the type of other features that are really important to have. And let me just kind of say very, very fast things about them. For the GUARD program of guaranteeing AI, it's very important to notice that we found that explainable AI is not the final answer to protect AI, because in fact, you can train the system to be explainable and to explain to you wrong things. So if we want to know if the situation needs human intervention and the system wants to tell you no, it will tell you no, and it will say because all inputs are in the range of what AI can do very well. So it learns how to reason for you. So it can continue doing that. And it's a trick. It's not just explainability is not sufficient. The other thing that people use sometimes, or suggest to do sometimes, is to compute the confidence. And confidence can be computed as that the class that you choose is much more sure than all the other classes. And also it's easy to attack. So we can also attack confidence. So when we talk about protecting lifelong learning, we really need to think much more deeper about what we suggest. Let's put the human in the loop. So there is a method that my postdoc suggested, and actually has a patent from the last year. I'm not sure what we'll do with the patent, because none of us is an industrial person. I think at the time he thought to go to industry, but now he became a professor, so he will not. And the notion was that we can take a screen, or we can take a word and put frames on. So you see, I just defined frames on the different things. And we can have a system that helps operator where to look. So in reality, we can have an operator move its focus from place to place, and the way where to move and how to move is being hinted by the system. So in that way, a human can help exactly where it's needed, and it's not needed all the time, and it kind of can move around and get used to the hints. And this seems to work very, very well. So we're just doing.
Sorry, have 1 minute. We should start wrapping up.
We have 1 minute. Okay, not a problem. So let me just finalize it here with my last slide. That, yeah, these slides were behind the last one because I didn't know how much time I have. So this is really to end the talk, that it's possible that in a few years, what we call today AI will not be considered intelligent without lifelong learning. And as an example, if one person needs a prosthetic, it wants to be trained in factory, but it also wants to be trained from the person, and also to be ready for emergencies if weather changing or something that is out of habit. So with that, thank you so much for inviting me, and I'm going to stay here to listen to the other speakers.